Progress is impossible without change, and those who cannot change their minds cannot change anything. Hi, all. Dr. Clark here again, and we're going to continue with the scientific method. Before I do that, though, I'll take my mask off and return my head back to you guys. I just thought it might be funny to look at. Anyhow, last time we talked about the scientific method, and I went over the steps of the scientific method, and I told you we're going to practice the scientific method quite a bit this school year. So look forward to different ways at which we're going to do that. At times we're going to create our own experiments. Other times you're just going to analyze other people's experiments and did they follow the scientific method. I assure you, knowing the scientific method back and forth is very valuable regardless of the course, whether it's environmental science, chemistry, physics, biology, even psychology. These fields use the scientific method, and it's important to know the steps. So let's dive into a little bit about using the scientific method. Okay, so let's talk about the first vaccination. This is important. This is kind of a component in today's society, with COVID and the possibility of having a vaccination, the possibility of not having a vaccination for a long time. Okay, but let's talk about the very first vaccination. Okay, so smallpox was a deadly disease, and I can say that it is a deadly disease. So if we were to allow smallpox to come back, it would be still a deadly disease. Now, because majority of people have received the vaccination and the virus itself is very low. Now, there are some examples of smallpox being around still in other animals. And that's one of the things that makes COVID kind of dangerous, is that it can be transferred to other animals, and other animals can hold COVID-19 in their system, like cats and bats and most likely dogs. I haven't seen too many reports on that, but there are other organisms that can hold COVID-19. So anyways, back to smallpox. So smallpox, first vaccination, okay? When we talk about smallpox, it was lethal. I mean, far more lethal than COVID is, with about a 30% fatality rate. But given that fatality rate, it was very important for vaccinations to be discovered. And just like COVID, it's still very important for vaccinations to be discovered. And it was Dr. Edward Jenner who discovered the first vaccination, and the vaccination for smallpox. Okay? And he did so by examining this, or using the scientific method. So just to kind of gross you out, this is a picture of someone with smallpox. Very painful blisters that form across the entire body. Those blisters fill with fluid. That fluid can then pass on smallpox to another individual. This is a very horrible disease. So much that white people used it as a biological warfare. Okay? And so there is many documentations of whites, when we went to the United States or the New World, that we would bring blankets and other things that people with smallpox had been laying on or exposed to. The blisters had burst onto these blankets, and we'd bring them to the Native Americans, and we'd trade those blankets with the Native Americans. So even though the death rate was somewhere around 35%, when we start looking at the mortality rate of other individuals, and we're going to talk about this in class. So just because we say, hey, a death rate is this, or hey, the poverty rate is this, or the pollution rate is this, we have to look at it at individual pieces, because the average, sure, might be 30%, but if you're, from the Mandan tribe, it's 90% of your population's going to die. From the Taino tribe, 100%. It wiped out the entire tribe. So yes, maybe it was 30% across everyone. Okay? But when we start talking about smaller groups of people or different genetics of individuals, right, maybe that is a more telling story. We don't want entire gene lines to be wiped out of the planet. And so is COVID more, does it have a higher death rate for individuals of different genetics? We don't know yet, because it's such a new disease. But if it does, then we need to think about that. Okay? Does pollution affect individuals of different genetics or different different levels of economics? So if you're poor, do you experience pollution more often than if you're wealthy? We're going to look into these things, because just because you have an average rate of pollution, or you have an average rate of a disease, or the average, yes, it tells us the big picture. But what's the small picture? Who's being affected more heavily by some of these things? And that's also important to keep in mind. So let's look at this first vaccination, the scientific method. So, of course, Jenner had done observations and gathered general information, general facts. And one of the general facts is that dairymaids, or women who often milked cows or even lived with cows. So at the time when, smallpox was a big deal, okay, and Jenner's work was, scientific work was coming out, okay, a lot of people would live with their livestock. So the cows, the sheep, things like that, they would live in your home. Mainly because you didn't have elaborate homes and things like that, and you might not have enough resources to build a separate barn, but also if the cow's living next to you or in the same vicinity of you, it's easy to protect it from predators. It's easy to, feed it. It's also easy to milk it in poor weather and other things. So often the livestock would live with them. Well, dairymaids that got cowpox, which is a cousin to smallpox, they seem to be protected from smallpox. And so Jenner noticed this, and he noticed that these mainly women that were milking cows on a day-to-day basis and had contracted cowpox seemed to be protected from smallpox. So that was the general kind of observation, and so then he started thinking, can I expose people to cowpox in order to get them to be, not affected by smallpox? So his hypothesis was then this preliminary explanation was then, if I expose people to cowpox, they would become immune to smallpox. And you notice that Jenner's hypothesis is not a question. It's a statement. And it's a directive statement. So if a person was exposed to cowpox, they would become immune to smallpox. It's not a tentative, sitting on the fence statement. It's not, if I expose people to cowpox, then maybe they'll be immune to smallpox. That's not how a hypothesis works. A hypothesis is cut and dry. You have to be able to test it. You can't say maybe, or you can't say it would slightly, or you can't have this ability to opt out. Okay? It's one way or another. Right? And that's the reason why it's one way or another is because these hypotheses are tested, and then that material is then analyzed by statistics. And statistics, because it's math, okay, there's a right answer and there's a wrong answer. Okay, there is a cutoff mark. And there's a cutoff mark for your hypothesis being supported, and there's a cutoff mark for your hypothesis being refuted. Okay? And so that's why hypotheses need to be set up as direct statements that are testable. Okay, so that's Jenner's original hypothesis. Okay, so he had to devise an experiment to test that hypothesis. Okay, so experiments, again, test hypotheses, and good experiments have good controls, and they control for many conditions, and they're carefully designed to test typically a single variable at a time. What kind of variables are we talking about? Okay. These are going to be important because you're going to need to learn how to set up experiments, but also how to set up data that has already been collected for you. And set up, I mean, how do you visualize that data? Do you put it in a bar graph? Do you put it in a line graph? Do you put it in a pie graph? Okay, what does it look like in a table? These kind of things are important for analyzing data. So we're going to talk about two types of variables, two main types of variables. Independent variables. These are factors or conditions, okay, that can be introduced and tested. Okay? And so it'll make more sense when I talk about dependent variables. Okay? Dependent variables are the result of independent variables. Okay? And so dependent variables are dependent on the independent variable. Okay? Now that might not sound, it might confuse you, but you think about it this way. An independent variable would be something like a date. So I could say the date is August 12th, 2020. Okay? And then my dependent variable could be the temperature of that day. Okay? Now, you would say August 12th, 2020, okay? And the temperature is the dependent variable, not vice versa. Because let's flip that around and say the independent variable was the temperature, and the dependent variable is the date. So then it would say the temperature, let's say the temperature was 94 degrees, then it would say every time the temperature is 94 degrees, it is August 14th, 2020. See, that doesn't make sense, okay? Because the temperature is not directing or is not telling you what the independent variable is. The independent variable is telling you what the dependent variable is. Okay? We'll come back and we'll look at a lot of these so you can set them up on a graph and you can understand what the variables should be and where they should be on the graph. Okay? The other variable that we often don't talk about but are kind of important is controlled variables. Okay? And the more controlled variables you can have in an experiment, the better. So the more variables you can control for, the better your experiment will be. So let's say that you want to examine, well, a new vaccination. Okay? Let's say you're trying to figure a COVID vaccination out. Okay? So you want to control for variables, okay, in your experiment. And as many as you can would be perfect. Okay, so you want to control for individuals that have other conditions. Okay? You want to control for side effects that the drug might have. What happens if someone can't read the label and they take too much? Okay? What happens if they take too little? What happens if they take it with alcohol? What happens if they take it, while doing another drug? Okay? These are all variables that you have to control for when you're devising a new type of medicine. Okay? This is why it takes so long for individuals to come up with new vaccinations or new drugs, because you have to go through and try to control for as many variables as possible. You would control for age, the sex of the individual, even the race of the individual. Okay? Possibly, it'd be important to control for the diet of the individual. Okay? So there's lots of roles that human trials got to go through when we're talking about drugs. Okay? So here you can see just a simple setup of a graph. Okay? So we could put lines on this, we could put bars on this, we could put dots on this. Okay? And the way a graph is typically set up is the independent variables are on the x-axis. So a lot of independent variables would be things like time, okay? Dates. Temperature can be an independent variable, and it often is an independent variable. Categories. Okay? These things would go on your x-axis. And on your y-axis is the dependent variable. What are you measuring? Okay? How did the temperature change an organism's behavior? Okay? How did the date change when an organism wakes up? Okay? How does the year change how much ice is on the polar caps? Okay? Categories. There's lots of categories. Males. How are males, more aggressive than females? So there are lots of variables, dependent variables, things that you are going to measure that would go on the y-axis. Okay, and we'll come back to many of these to practice. We're going to practice quite a bit so you understand what an independent variable is versus a dependent variable is. Okay, at first it can be very confusing. Okay, so let's go back to Jenner's work. So Jenner experimented, with an 8-year-old child. Okay? And he would give that 8-year-old child cowpox. Okay? So he allowed the 8-year-old to get cowpox, okay? Let the infection go away, and then gave the child cowpox again. Right? So he did this a few times, and then he gave the child smallpox. Okay? So let's look and think about what's the independent variable. Okay? What's independent? What has no effect or you're not measuring? Okay? The vaccine. The vaccine hasn't changed at all. Okay? That's your independent variable. What is your dependent variable? The dependent variable is, was the patient protected from smallpox? Okay? Did the 8-year-old show immunity to smallpox? Okay. The constant variables, now this is kind of difficult because he only experimented on one child, but that's the constant variable. It's a single child who had never had smallpox. Okay. And so we'll talk about experimental design, but the initial experimental design was not well thought out because he only had one kid that he worked on, or the sample size was one. Okay? And we're going to look at what you need to have as a sample size. So the boy survived 20 inoculations without succumbing to smallpox. Okay, so cowpox, he got cowpox, gave it to cowpox to him again, and then started inoculating the boy with smallpox. And the smallpox did not affect the boy. Okay, so the conclusion from his experiment, okay, now he didn't do a bunch of data analysis because his sample size was one boy. Okay, he didn't do a bunch of statistics and things like that, but he could come to a conclusion, and that was that, this vaccination of vaccinating with cowpox supported his hypothesis, okay, that if you give someone cowpox, they'll be immune to smallpox. Okay. Now, one key component that I want you to remember, this doesn't prove anything. Just because the hypothesis is supported does not mean that it's proven. Scientists do not prove hypotheses. They don't prove theories either. Okay? Now, in some cases, you can prove a law. Okay? But for the most part, scientists don't prove anything. They just support it with evidence. The more support you have, the better that hypothesis is. The more support you have, the better that theory is. So, Jenner's final step to this scientific method was communicate your results. So he published the results in the Royal Society of Medicine, but because publications are reviewed by other scientists and other individuals, other doctors, okay, they reviewed it and they said, hey, look, man, one child, that's not enough. That's not enough proof. Go back, see if you can repeat it with more samples. Okay. Now, Jenner did this, and we're going to talk about that. But in the meantime, okay, people got a hold of this medical journal that he published, and they started making all kinds of cartoons around this. During this time, it's pretty common in the 1800s and whatnot, 1700s, it's very common to make comics about things. That's how people kind of ridiculed other people's work. And so you can see here, there's a doctor that's giving the vaccination, cowpox vaccination, and these people have got it, and as they're walking away, they're growing cows out of their eyes, their ears, their nose, okay, their rear end, etc. And, you have all these other people coming in that are sick. And so, they're really poking fun of this cowpox vaccination. But in the end, you have to examine your sample size, or, how many samples you've collected, because in some cases, maybe if you're only examining a sample size of 1, maybe the boy was already immune to smallpox to begin with. Okay? You would never know that that individual, that 8-year-old, was already immune to it because he had never had it before. Okay? So that's why you need to have a lot of data, a lot of samples, is because you don't know if there's immunity by that individual's genetics, or you don't know if that tree would have grew there regardless of the habitat. Okay? So margin of error is a good measurement to estimate the amount of random error that you can expect. Okay? And so when we talk about statistics, and we talk about statistics in environmental science, we normally use a margin of error of 5%. Okay? We're okay with 5% error, which means that you're 95% confident, okay, that something is true. So let's say we were doing that cowpox vaccination and we had 100 people. and we had 5 people it didn't work on, and they still got smallpox. We're okay with that because 95% it worked. That means you have a significant result. You can publish that result, and the experimental design and other things were good. Okay, so we accept in environmental science, we accept 5% error. The more samples you have, the less error you're going to have. Okay? And we can do a great example of this, and I want you to do this, okay, example at home. Okay? I want you to take a coin, okay, and I want you to flip that coin 4 times. Okay? So a fair coin, whether it be a quarter, a penny, whatever, a fair coin that has a heads and tails, flip it 4 times. Now, you would expect 2 of them to be head and 2 of them to be tails. Okay? That's what you'd expect because it's fair and it's 50-50, right? Okay? I would argue that most of you will not get 2 heads, 2 tails. Okay? Now take that coin and flip it 10 times. You'd expect 5 and 5. I still think you're going to be hard-pressed to get 5 and 5. But now, flip it 30 times, and you'll be very close to 15 and 15. Okay? So we're going to do that in an activity, and we're going to run some statistics on it. But, before we get to that, go ahead and try it yourself and see what you get. Okay? That's where sample size comes in. The more times you flip it, the more data you collect, the closer it will be to that 50-50. If you were to sit there and flip it 1,000 times, you're going to be very close to 500 heads and 500 tails. Okay? And it's really something that we call the law of probability. Okay? That as you increase sample size, the margin of error decreases. And that's why even in scientific experiments, we have to have more than one. And typically, the cutoff is 30. So as an environmental scientist, as an experimental biologist, okay, the cutoff for the minimum you should have, samples you should have, is 30. So Jenner was able to locate several other parents who were willing to volunteer their children. Okay? He even volunteered his own child. Okay? After he had more results, okay, and more immunity to smallpox, Jenner finally published it. Okay? It was accepted, and he called the new technique vaccination, okay, which is comes from the Latin word, or the root of the Latin word, which means cow or vacca. Okay, and so here you can see Jenner, inoculating these children with, at first cowpox, and then trying to inoculate them with smallpox. Okay, so experimental design is very important, okay, and it's needed. A good experimental design is needed to be able to support or refute your hypothesis. Now, sometimes controlled experiments are not possible. Okay? Think about it. So let's say we're examining whether or not glaciers in North America are receding due to global climate change. Well, what's our control? I mean, yeah, we can look at pictures and things like that from the past. We can't travel in the past. Okay? And we don't have another planet to say, hey, let's reduce the carbon dioxide on this planet and see if that helps with global climate change. So controlled experiments are very difficult and many times very difficult for environmental science. So sometimes what we do is we have to set up those experiments in small stature, okay, in small units like a terrarium, okay, or a biodome. Okay, so you might know from Arizona, you might know that Arizona set up a biodome. Okay? That was to try to look at some of these experiments and control for some of those factors, because you can't control those factors in the world setting. So if you could build yourself a little world and do it that way, then you can control for different things. Okay? So often natural experiments or experiments that are conducted in the field, there's very little controls that you can set up. Okay? Now there's advantages to this, because if you're looking at the behavior of an organism, or where a certain plant grows, or how fast a certain pollution can penetrate into the soil, okay? It's a real world issue or a real world circumstance. Okay? If you're doing that in a lab and everything is controlled, okay, it's often best case scenario. Okay? But if you're doing it in the environment and you're saying, okay, well, how fast can oil penetrate this soil if we have an oil spill? Okay? You can do that in the lab, and you can see how fast the oil would penetrate and get into the water system. Okay? But if you did that in a natural experiment, okay, and it rains that day, or it's 100 degrees out that day, or there's vehicles driving over the oil spill, okay, now you have real world normal circumstances that would be occurring, or wind blowing across it, normal circumstances that would be occurring that are going to affect that penetration through the soil. Okay? So it's a little more realistic, but it's also harder to predict. And there's some situations where you just can't predict or find or design an experiment to run at that exact moment in time. Okay? So if we're trying to look at the effects of a hurricane, okay, or the effects of an earthquake on something, or the effects of a tornado on something, or a monsoon on something, well, you might be sitting around for a long time before that would occur. And is that going to occur at the exact moment in time or the exact spot that you need it to occur? Probably not, okay? And so sometimes those natural phenomena, if that's what we're interested in, they're just very difficult to predict, and they're very difficult to set up experiments around. Okay? So field biologists or field ecologists or environmental scientists that do field work, they often rely on long-term studies, okay? Being able to collect data for a very long period of time and then looking at trends in the data. Okay? For example, Jane Goodall, who is pictured here, okay, she lived with chimpanzees and gorillas. Okay? She studied them every single day for years to be able to look at facial expression, behaviors, communication, diet. Okay? And she's known as the world's expert on primate biology and primate ecology. But it took her years and years and years of research to do that. Think about changes that might occur in the Earth's atmosphere or the Earth's temperature. Okay? Let's say we're looking at global climate change and we want to predict what might happen. Well, yes, the climate is changing, but it's only warmed about 2 degrees Celsius in the last 50 years. Okay? So if you're a environmental science and you want to look at the effects of that 2 degrees of warming on a forest that you work in, you're going to have to wait 50 years to see that effect. Okay? So that's why, like I said before, it's important to collect data in a uniform way, publish your data so scientists that come along can then use your data and they don't have to restart the entire experiment. They can start where you left off. Okay? Because most scientists aren't doing science for 50 years, 60 years, 70 years. They're not doing the same experiment. Okay? But if you have a good scientific design and you use a scientific method, then people can pick up after you're done and they can continue that research into the future. Okay, so we're going to stop there and we're going to come back and we're going to talk about biases and how we combat biases.